Every map of the moon you have ever seen is a lie, not an innocent omission, not a gap in our knowledge, a deliberate structural feature of the universe itself, one that has kept an entire hemisphere of our closest neighbour hidden from human eyes for the entirety of human existence. And when we finally looked, when we finally sent our instruments to peer at what the moon had been concealing for 4.5 billion years, we found something that violated the most fundamental assumptions we held about how worlds are made. Something that should not be there. Something that rewrites the origin of the moon itself. For as long as human beings have existed on this planet, the moon has shown us exactly one face. That fact is so familiar, so woven into the fabric of daily experience, that most people never stop to ask why. Why does a world orbiting ours rotate in perfect lockstep with that orbit, presenting the same hemisphere always, without variation, without drift? Is it coincidence? Is it design? The answer is neither. It is physics, and it is as inevitable as gravity itself. The phenomenon is called tidal locking. Over billions of years, Earth's gravitational pull created tidal forces inside the moon, not ocean tides, but solid rock deforming under gravitational stress, that gradually slowed the moon's rotation until it matched its orbital period exactly. 27.3 days to orbit Earth, 27.3 days to rotate once on its axis. The result? One face perpetually toward us, one face perpetually away. A permanent turning of the back maintained without fail for billions of years. Ancient civilizations built entire mythologies around the visible face. Every culture that looked up found meaning in its craters and plains. The man in the moon, the rabbit of Chinese and Mesoamerican tradition, the goddess Diana, the Norse figure of Mani. Philosophers speculated about what might exist on the hidden side. Might it have a different character, a different composition? Some imagined it mirrored the near side. Some imagined it was perfectly smooth. Some, in the more fanciful reaches of pre-scientific thought, imagined it harboured another world entirely. None of them came close. The space age arrived in the 20th century, and with it, finally, the ability to look. On October 7th, 1959, the Soviet spacecraft Luna 3 swung around the moon on a carefully calculated trajectory and trained its camera on the far side for the first time in history. The images it returned, grainy, low resolution, chemically developed inside the spacecraft and then transmitted by analog signal, were nonetheless extraordinary. Scientists crowded around the printouts, and what they saw immediately raised a question that has not been fully answered in the 6 decades since. The near side of the moon, the face we see, is characterized by vast dark plains called Maria. In Latin, the word means seas, a name bestowed by early telescopic astronomers who mistook their dark color for standing water. These Maria are ancient volcanic plains, formed by massive eruptions of basaltic lava billions of years ago. They cover approximately 31% of the near-side surface. They're expansive, relatively flat, and geologically distinct from the heavily cratered highlands surrounding them. Look at the far side. The Maria cover barely 2% of the surface, 2% versus 31%. One face dramatically darker, smoother, more geologically active in the ancient past. One face overwhelmingly covered in pale, battered ancient highlands, some of the oldest terrain in the entire solar system, a tortured landscape of craters upon craters upon craters, an unbroken archive of every impact event the inner solar system delivered over 4.5 billion years. Why? Why would two hemispheres of the same world be so profoundly, so structurally different? This is not a subtle variation. This is not the kind of difference you explain with minor geological variations or slight compositional differences. The two sides of the moon look, in fundamental ways, like they come from different worlds. The disparity is so dramatic that planetary scientists gave it a name, the lunar dichotomy. For 60 years it has sat at the centre of lunar science as one of the most profound and unresolved mysteries in planetary geology. But in January of 2019, something happened that transformed the lunar dichotomy from a theoretical puzzle into a site of active, urgent investigation. China's Chang'e 4 spacecraft did what no mission had ever done before. It landed on the far side of the moon. Not an orbit, not a flyby, a landing. Wheels, or rather landing legs, touching ancient rock that no human-made object had ever touched. In a region of the Moon that cannot be seen from Earth, cannot communicate directly with Earth, requires a dedicated relay satellite positioned at the gravitationally stable L2 point of the Earth-Moon system, just to maintain contact. The mission required engineering solutions that didn't exist before China built them. The landing site was the von Karman crater, a 186-kilometer wide ancient impact basin, nestled within the South Pole Aitken Basin, the largest, deepest and most ancient impact structure on the Moon. The South Pole Aitken Basin. These 5 words will become important. Remember them. At approximately 2,500 kilometers in diameter and up to 8 kilometers deep, the South Pole Aitken Basin, SPA Basin for short, is not just the largest crater on the Moon. It is one of the largest confirmed impact craters in the entire solar system. It dwarfs every other structure on the lunar surface. Its floor sits so far below the surrounding terrain that it creates its own micro-environment of perpetual shadow in some locations. Its rim walls rise kilometers above the surrounding plains. The impact that created it was, by every measure, a planetary-scale catastrophe, an object perhaps 170 kilometers in diameter, striking the early Moon at tens of kilometers per second, excavating a hole in the lunar crust so deep it very likely penetrated through the crust into the mantle beneath. What the mantle holds is the key to everything that follows. Chang'e 4's Yutu-2 rover, the Jade Rabbit 2, a name steeped in Chinese lunar mythology, rolled onto the ancient surface of von Karman crater and began its survey. Its instruments included a visible and near-infrared spectrometer, designed to analyze the chemical composition of the rocks and soil around it. What it detected in the first weeks of operation sent its data back through the Queqiao relay satellite to mission controllers in Beijing, and from there into a paper published in the journal Nature in May of 2019. The mantle material was there, right there, on the surface, mixed into the ancient regolith, the fine ground rock that blankets the lunar surface like powdered history. Olivine and pyroxene, minerals that in lunar geology are the signature of the deep mantle, exposed by the titanic excavation of the SPA Basin impact, and now sitting on the surface waiting for a rover to drive across them. This was significant. More than significant, it was the first direct sampling of what appears to be lunar mantle material, answering a question planetary scientists had been asking for 50 years. It told us that the impact that formed the SPA Basin was even more violent than modelled, that it punched through the crust with terrifying efficiency, that the early Moon was struck by something large enough to fundamentally reshape a world. But that's not the full story, because as the data from Chang'e 4 was analysed, as subsequent missions added their own measurements, as Earth-based radar and orbital instruments were brought to bear on the far side in new ways, a pattern emerged. A pattern that didn't fit the existing models. A pattern that pointed not just to an ancient impact, but to something buried beneath the SPA Basin that had no business being there at all. Something dense, something cold, something of a scale that, when its true nature was finally proposed in a 2019 paper by researchers at Baylor University, prompted one of the lead authors to describe it as, in his words, one of the most unexpected discoveries in lunar science. What scientists found next would shock even the researchers who made the discovery. Let's establish the baseline of what we thought we knew about the Moon's interior. Planetary science operates from a principle called differentiation, the process by which a young molten world sorts itself by density, like a cosmic salad dressing separating in a jar. Heavy materials, iron, nickel, sink toward the center, forming a core. Lighter silicate rocks rise toward the surface, forming a crust. In between sits the mantle, a thick shell of partially molten or solid rock, denser than the crust above but lighter than the core below. For Earth, we have mapped this internal architecture in extraordinary detail using seismology, the science of studying how earthquake waves propagate through the planet's interior. Different rock types transmit seismic waves at different speeds and in different ways. By tracking how waves from earthquakes travel through Earth, scientists have built a three-dimensional picture of everything beneath our feet, from the crust down to the solid iron inner core 6,371 kilometers below the surface. For the Moon, we have significantly less seismic data. The Apollo missions installed seismometers on the lunar surface, 4 of them, or operating from 1969 through 1977, and those instruments recorded thousands of moonquakes and meteorite impacts, providing a foundational dataset for lunar seismology. From that data, scientists built a model of the lunar interior, a thin crust averaging roughly 50 kilometers thick, a mantle extending down approximately 1,500 kilometers, and a small iron core perhaps 300 to 400 kilometers in radius. It was a reasonable model, consistent with the data, consistent with theories of how the moon formed, and it had one significant problem. It didn't fully account for the lunar dichotomy, the dramatic difference between the near side's volcanic plains and the far side's ancient highlands. The model said the moon should be broadly symmetric. The moon clearly was not. Multiple explanations for the dichotomy had been proposed over the decades. One early hypothesis, the double impact theory, suggested that Earth originally had two moons, and they collided in slow motion, the smaller accreting onto the far side of the larger and forming the thicker, highland-dominated crust we observe there. A thicker far side crust would have resisted the volcanic eruptions that flooded the near side with basaltic maria, producing exactly the dichotomy we see. This theory was proposed by Eric Asfaug and Martin Jutzi in 2011 and attracted serious attention, though it remains contested. Another explanation focused on heat. The near side of the moon faces Earth, and in the early solar system, Earth was a much hotter body, still glowing from its own formation, and the Theia impact that created the moon in the first place. Might the heat differential have kept the near side mantle warmer longer, sustaining volcanic activity there while the far side cooled and solidified? Thermal models suggest this could have played a role, but the magnitude of the effect doesn't fully explain the dichotomy on its own. A third explanation, proposed in various forms over the years, involved the distribution of a peculiar family of rocks found in the lunar highlands and Maria. These rocks are unusually enriched in potassium, rare earth elements, and phosphorus, a chemical signature that planetary scientists abbreviate as CREEP. CREEP-rich material is concentrated on the near side of the moon, particularly around a region called Oceanus Procellarum, the vast dark plain visible to the naked eye on the upper left quadrant of the full moon. The heat-producing radioactive elements within CREEP material could have kept the near-side mantle warm and volcanically active for far longer than the far side. But where did all that CREEP come from? Why is it concentrated on the near side? That question connects to the original event that created the moon, and to the hidden structure beneath the far side that China's mission had just begun to reveal. Here is a number to hold in your mind: 2.18 quintillion kilograms. That is the estimated mass of the anomaly, the thing that shouldn't be there, detected beneath the South Pole Aitken Basin by Peter B. James and his colleagues at Baylor University, using gravitational data from NASA's GRAIL mission. GRAIL, Gravity Recovery and Interior Laboratory, consisted of two spacecraft, Ebb and Flow, that orbited the moon in 2012, measuring infinitesimally small variations in the moon's gravitational field by tracking tiny changes in the distance between the two probes as they flew in formation. Gravitational variations reveal mass concentrations beneath the surface. A large, dense structure buried under the crust creates a slightly stronger gravitational pull that perturbs the orbits of spacecraft passing overhead in measurable ways. GRAIL was sensitive enough to detect mass anomalies, equivalent to buried geological structures kilometers below the surface, with extraordinary precision. And it found something beneath the South Pole Aitken Basin that the models didn't predict. A mass concentration, a mascon in the technical terminology, so large that it extends from the surface down through the crust and deep into the upper mantle. In horizontal extent, it covers an area roughly the size of the entire island of Hawaii in a geographic sense, but in mass terms, it is almost incomprehensibly large. 2.18 quintillion kilograms of excess mass, over and above what the existing rock in that region would account for. To put this in perspective, 2.18 quintillion kilograms is roughly the mass of the entire ocean of water on Earth's surface. Every drop of every sea, every river, every lake, every glacier and ice sheet and raindrop in the atmosphere. Imagine taking all of Earth's water, condensing it into dense metallic rock, and burying it in the mantle of the moon. That is the scale of what is sitting beneath the far side. Now here's where it gets truly strange. The leading explanation for this anomaly, the one that Peter James and his team proposed in their 2019 paper in Geophysical Research Letters, is that it is the remnant core of the asteroid that created the South Pole Aitken Basin, the impactor itself, not scattered, not vaporized, partially embedded, sitting in the lunar mantle like a bullet lodged in bone, still there after 4 billion years. The implications of this discovery are almost too vast to comprehend. An asteroid core, buried in the moon, intact enough to register in gravitational data 4 billion years after impact. That single sentence collapses the distance between abstract planetary science and visceral, physical reality. This is not a chemical signature, not a slight compositional variation. This is a foreign object of staggering mass. Embedded in the body of our moon, sitting 40 kilometers beneath the surface of the South Pole Aitken Basin, and detectable only because its density warps the gravitational field enough for a spacecraft to notice. How is that possible? Standard impact physics, the models built on computer simulations and validated against cratering records across the solar system, predict that a hypervelocity impact large enough to carve the South Pole Aitken Basin should have obliterated the impactor. At impact velocities of 15 to 20 kilometers per second, the kinetic energy released is measured in the same units as thermonuclear weapons. Just billions of them, all detonated simultaneously. The impactor should have vaporized. The target rock should have vaporized. The entire event should have produced a vast cloud of superheated plasma and debris, the same kind of event that is believed to have created the moon itself, and yet the mass is there, unmoved, unscattered, buried. The resolution to this apparent contradiction lies in the specific geometry and velocity of the impact. Not all impacts are equal. A particularly slow impact, slow in relative terms, perhaps 12 kilometers per second rather than 20, combined with a low impact angle might allow a substantial fraction of the impactor's core to survive and embed in the target body rather than fully vaporizing. The iron-nickel core of a differentiated asteroid is far denser and far more resistant to shock than the silicate rock of its mantle. In the right conditions, it could plow through the target's crust and lodge in the mantle, retaining its structural integrity even as the surrounding rock melted and flowed around it. Think of it this way. Drop a steel ball bearing into a tank of ballistic gelatin at high speed, and it will penetrate deep into the gelatin and stop, embedded, intact, surrounded by the medium it tore through. Scale that concept up to planetary dimensions, replace the gelatin with the lunar mantle, and you have a rough analogy for what appears to have happened beneath the South Pole Aitken Basin. But the embedded core hypothesis raises its own cascade of questions. If the impactor's core survived the collision, what happened to the rest of it? The mantle of the impacting asteroid, the lighter silicate rock surrounding the iron core, would have been stripped away during impact, liquefied, mixed with vaporized lunar rock, and distributed across the surrounding terrain and into space. Some of it rained back down onto the lunar surface, some was blasted into Earth orbit, some escaped the Earth-Moon system entirely. This redistribution of impactor material is not merely a geological curiosity, it may hold the key to the lunar dichotomy itself. Remember the creep enrichment we discussed, those near-side concentrations of potassium, rare Earth elements, and phosphorus that seem to drive the dramatic difference between the two hemispheres? Creep material is believed to have formed from the last dregs of the lunar magma ocean, the global ocean of molten rock that covered the entire moon in the first 100 million years after its formation. As the magma ocean cooled and crystallized, denser minerals sank and lighter ones floated upward, forming the crust. The incompatible elements, the ones that don't fit neatly into crystal structures, were concentrated into the residual melt that remained liquid longest. That residual melt is what became Keep. If the SPA Basin impact excavated deep into the moon shortly after the lunar magma ocean had crystallized, it would have redistributed enormous quantities of creep-rich material across the lunar surface. The trajectory of that redistribution, controlled by the impact geometry in the moon's rotation, could explain why creep concentrations are so heavily weighted toward the near side. This connection, between the buried impactor beneath the far side and the volcanic history of the near side, suggests that a single ancient impact event may have set the stage for everything that followed in the moon's geological story. The Maria we see when we look up at the moon on a clear night, the creep-driven thermal anomaly that kept the near-side mantle warm and productive for 1 billion years, The ancient highlands of the far side never flooded by lava because the crust there was simply too thick for eruptions to breach. All of it, potentially, a consequence of one catastrophic collision 4 billion years ago. What does this mean for our understanding of the solar system? Consider the timing. The SPA basin is believed to have formed approximately 4.1 to 4.3 billion years ago, a period in solar system history called the Late Heavy Bombardment, when the inner solar system was being pummeled by an extraordinary flux of impacting bodies. The reasons for this bombardment are tied to the migration of the giant outer planets, Jupiter and Saturn, whose gravitational interactions destabilized the asteroid belt and sent vast numbers of planetesimals plunging into the inner solar system on chaotic orbits. The Moon's heavily cratered far side is a direct record of this bombardment. Every crater there, and there are thousands, overlapping and nested and stacked on top of each other in a geological palimpsest stretching back to the solar system's violent adolescence, represents an impact event from that era. The Moon's far side is in this sense a 4 billion year archive of the most violent period in Earth's neighbourhood. And buried at the bottom of the deepest archive beneath the oldest and largest crater of all sits the remains of the asteroid that started it all. Or did it? Because the embedded core hypothesis, compelling as it is not the only explanation for the SPA basin mass anomaly. A competing model proposes something different, and in many ways, even more fascinating. Some planetary scientists argue that the mass concentration beneath the SPA basin is not an impactor core at all. Instead, it represents a concentration of dense oxides that crystallized out of the lunar magma ocean in the region beneath the impact site. The SPA impact on this interpretation excavated the crust and decompressed the underlying mantle, triggering a flow of dense material from the deeper mantle upward into the region beneath the crater, a process called dynamic rebound, familiar from smaller impact craters where the floor rebounds upward after the initial excavation. If the mass anomaly is magma ocean crystallization products rather than impactor material, the timeline is different, the composition is different, the implications for the lunar dichotomy are different, and the story of what the far side is hiding is different in kind, not just degree. Right now, in 2026, we cannot definitively distinguish between these two explanations from orbit. The Grail data tells us the mass is there, and gives us its approximate distribution. It cannot tell us what it is made of. For that we need seismology, the measurement of moonquakes propagating through the far side mantle, and potentially direct sampling from depths no mission has yet reached. Which is why what is being planned for the Moon in the next decade may be the most scientifically significant program of exploration since Apollo. The implications of this discovery, whether the mass is an impactor remnant or a magma ocean product, are almost too vast to comprehend. Because either answer reshapes our model of how the Moon formed, how it evolved, and how our own planet was shaped by the same violent forces operating in the early solar system. Here is where everything converges. To truly understand what the far side of the Moon is hiding, we need to go back. Not just to the formation of the Moon, but to the formation of the entire Earth-Moon system. Because the anomaly beneath the South Pole Aitken Basin is not an isolated curiosity. It is a thread, and when you pull it, it unravels the entire tapestry of how our world came to exist. The story begins approximately 4.5 billion years ago, in the early chaos of a solar system still assembling itself from the disk of gas and dust that surrounded the young sun. Earth exists, barely. It is a protoplanet, accreting mass from the cloud of debris orbiting the sun, growing hotter and denser with every impact, its surface a global ocean of magma thousands of kilometers deep. Violent, molten, unrecognizable as the world we know. And then something hits it. The Theia hypothesis, the giant impact hypothesis, proposes that a Mars-sized body called Theia struck the proto-Earth in a grazing collision of almost incomprehensible violence. Not a head-on impact, which would have destroyed both bodies, but a glancing blow, angled perhaps 30 to 45 degrees from the ecliptic plane. The collision released energy equivalent to hundreds of millions of nuclear warheads detonating simultaneously. Both bodies were partially vaporized. An enormous cloud of superheated rock vapor and molten debris was flung into orbit around Earth. And from that debris cloud, over a period of perhaps 100 years, impossibly fast on geological timescales, the Moon assembled itself. This model explains several features of the Earth-Moon system that were otherwise puzzling. It explains why the Moon has a relatively small iron core. Most of Earth's iron had already sunk to its centre before the impact, and the Theia collision primarily ejected mantle material into orbit. It explains why the Moon and Earth share identical oxygen isotope ratios. The two bodies mixed thoroughly during the impact. It explains the Moon's large size relative to Earth, unusual among planetary moons in the inner solar system. But here is where the story gets complicated, and where the far side anomaly becomes central. If Theia struck Earth in the way the standard giant impact model describes, the resulting Moon should be compositionally similar on all sides. The differentiation of the lunar magma ocean should have proceeded symmetrically, producing a broadly similar crust in all directions. Slight variations are expected from random processes. The magnitude of the actual dichotomy, 31% Maria coverage on the near side versus 2% on the far side, is not a slight variation. In 2022, a research team led by Matt Jones at Brown University published a reanalysis of the Theia impact model that introduced a significant modification. Their simulations, run on supercomputer clusters and tracking the fate of hundreds of thousands of individual particle interactions, suggested that the impact delivered a massive heat pulse asymmetrically to the forming Moon. The side of the young Moon facing Earth in the immediate aftermath of the impact was exposed to far greater thermal radiation from the still glowing debris cloud and the partially vaporized Earth itself. This asymmetric heating caused one hemisphere of the new Moon to remain molten far longer than the other, and in the crystallizing lunar magma ocean, the longer a region remains molten, the more creep and heat-producing radioactive elements concentrate in the residual liquid. The near side, perpetually facing Earth and receiving more heat, retained its liquid mantle longer. The far side cooled faster, crystallized earlier, and developed a thicker, more rigid crust. A thicker crust on the far side suppressed volcanism. A thinner, creep-heated crust on the near side drove it. The Maria formed on the near side, the highlands dominated the far. The dichotomy was set in this model, almost from the moment of the Moon's birth, a consequence not of a later impact but of the geometry of the original formation event. But then, into this already asymmetric young Moon, the SPA Basin impact arrives. Impossible. And yet, there it is, layered on top of the original asymmetry, deepening the far side's geological character, excavating through the far side's thick crust and exposing the mantle beneath, distributing material across the hemisphere in ways that reinforce every tendency already established by the formation asymmetry. The far side of the Moon has been shaped by not one but two fundamental geological events, each amplifying the effects of the other. The formation asymmetry set the stage, the SPA Basin impact, and whatever lies buried beneath it, defined the finale. Dr. Clive Neal, Professor of Planetary Geology at the University of Notre Dame and one of the world's leading advocates for a lunar seismic network, has argued for years that the key to resolving these questions lies in deploying a global seismograph network on the Moon, similar in concept to the global seismic networks that allow us to image Earth's interior. The Apollo seismometers were limited in number and confined to a small region of the near side. A properly distributed network, including instruments on the far side, would allow seismic waves from moonquakes to be used to construct a three-dimensional map of the lunar interior with a precision the Apollo data never achieved. That network is now within reach. NASA's Commercial Lunar Payload Services (CLPS) program has been contracting with private companies to deliver scientific instruments to the lunar surface as precursors to the Artemis crewed missions. Multiple seismometer payloads are in development. China's Chang'e program, following the landmark success of Chang'e 4, has continued with Chang'e 5, which returned the first new lunar samples to Earth since the Soviet Lunar 24 mission in 1976, and is planning Chang'e 6, Chang'e 7, and beyond. Chang'e 6, specifically targeting the South Pole Aitken Basin on the far side, launched in 2024 and successfully returned samples from that ancient terrain, the first ever far side sample return in history. Those samples, those small ancient pieces of far side regolith, now in laboratories in Beijing, they are the most scientifically valuable lunar material ever brought to Earth. Because the near side samples returned by Apollo came from the volcanic Maria and surrounding highlands, geological environments shaped primarily by the events after the Moon's formation. Far side samples from the SPA Basin come from a different category of time. They come from the earliest period of the Moon's existence, from terrain that formed in the immediate aftermath of the Theia impact and was then modified by the SPA Basin collision. Chemical analysis of these samples will allow scientists to date the SPA Basin impact with unprecedented precision, resolving debates about whether it occurred early in the late heavy bombardment or later. They will reveal the composition of the excavated mantle material, potentially distinguishing between the embedded impactor hypothesis and the magma ocean crystallization hypothesis. They will contain isotopic signatures, atomic fingerprints preserved in the rock since the solar system's formation, that tell the story of the Moon's birth with a resolution no remote sensing mission can achieve. Some might wonder why any of this matters beyond academic scientific interest. The answer is profound. The Moon is not merely our neighbour, it is a record keeper. Earth's geological processes, plate tectonics, erosion, the hydrological cycle, biological activity, have erased most of the evidence of the first billion years of our planet's existence. The ancient rocks that might tell us about the conditions under which life first arose, about the frequency of the giant impacts that sterilized and reseeded the early Earth, about the chemical environment of the primordial ocean. Most of that evidence is gone, overwritten by 4.5 billion years of geological activity. The Moon has experienced none of that. Its surface is, in large areas, essentially unchanged since the late heavy bombardment. The far side, with its ancient highland terrain, is even more pristine than the near side. Every rock in the SPA Basin is a page from the chapter of solar system history that Earth has lost. And that chapter may include the story of how life became possible on Earth. The late heavy bombardment that battered the Moon also battered Earth. Far more severely because Earth's larger gravity attracted more impactors, and because Earth's surface was a more dynamic target. But some of those impacts also delivered something beyond destruction. Carbonaceous chondrite asteroids, a class of primitive space rock rich in organic compounds, amino acids and water, were abundant in the early solar system and are well represented in the impactor population of the late heavy bombardment. The water in Earth's oceans, the organic chemistry that preceded life, the carbon that is the basis of every living thing on this planet. A significant fraction of all of it may have been delivered by the same bombardment that scarred the lunar surface. Look at the far side of the Moon, and you're looking at the aftermath of the delivery mechanism for life on Earth. This is the peak moment, the realization that changes the emotional register of everything. The far side of the Moon was not hiding something alien. It was not hiding a geological anomaly in isolation, interesting to specialists and obscure to everyone else. It was hiding the origin story, the physical evidence of the most important period in Earth's history, the violent, impact-saturated, chemistry-delivering early solar system that made us possible. Massive, ancient, impossible, remarkable. Every crater on the far side is a chapter, every basin is a volume, and the South Pole Aitken Basin, with its buried mass, its ancient excavated mantle, its billion-year-old impact melt, is the prologue to everything that followed. In January 2019, the same month that Chang'e 4 made humanity's first soft landing on the far side, the New Horizons mission, the spacecraft that had famously flown past Pluto in 2015, turned its cameras on a small ancient Kuiper Belt object called Arakoth. What it revealed was a contact binary, 2 lobes of primordial material gently touching, preserved in the cold dark of the outer solar system since before the planets had fully formed. The finding confirmed something theorists had long suspected, that accretion, the slow, gentle coming together of small bodies into larger ones, was the dominant mode of planetary formation in the early solar system. It validated the models. It reinforced the picture of a solar system that formed through accumulation, gradually, and then was subsequently modified by a period of violent giant impacts. The Theia impact that formed the Moon, the SPA Basin impact that modified its far side, the late heavy bombardment that delivered the chemistry of life to Earth. These were not random catastrophes interrupting an otherwise orderly process. They were the process. Violence and construction, chaos and order, destruction and creation, all intertwined, all necessary, all encoded in the ancient rocks of the lunar far side. The Moon kept this record for us, and now, finally, we are learning to read it. But this raises an even bigger question. If the far side of the Moon holds the geological record of the events that made Earth habitable, if it preserved the evidence of the impact bombardment that delivered water, organic chemistry, and the precursors of life, then what does it tell us about the probability of life elsewhere in the universe? This is not a rhetorical leap. It is a direct scientific inference. For decades, the search for life beyond Earth has operated on a fundamental uncertainty. We don't know how common the conditions for life actually are. We know life arose on Earth. We believe it arose relatively quickly after the late heavy bombardment subsided and conditions stabilized, perhaps as early as 3.5 to 4 billion years ago, within a few hundred million years of the surface becoming stable enough to support it. That's fast, almost suspiciously fast by astronomical standards. But fast relative to what? We have one data point, one planet, one example of life arising. From a single data point, you cannot determine a rate or a probability. You cannot know whether life is common in the universe or catastrophically rare. You cannot know whether the conditions that produced Earth, the right distance from the right kind of star, the right impact history, the right chemical delivery, the right planetary mass, are common or singular. The Moon's far-side record potentially helps us understand one crucial variable in that calculation: the role of the late heavy bombardment. If the bombardment was essential to delivering the chemistry of life, the water, the organics, the carbon, then life's origin on Earth is tied to a specific event in solar system history. And if that event was tied to the migration of Jupiter and Saturn, then the question becomes, how common is Jupiter-Saturn-like orbital architecture in other solar systems? How often does a system produce giant planets that migrate in ways that produce a late heavy bombardment? How often does that bombardment deliver the right chemistry to a terrestrial planet in the habitable zone? These questions are now answerable, at least in principle. The Kepler and TESS space telescopes have identified thousands of exoplanet systems, giving us a statistical picture of how planetary systems are organized. The architecture of our solar system, two giant outer planets in relatively circular orbits, a gap-free asteroid belt, terrestrial planets in the inner system, appears to be moderately common, not universal, but not exceptional, which suggests that late heavy bombardment events, perhaps not identical to ours but analogous, are a recurring feature of planetary system evolution. And if bombardments are common, and if bombardments deliver life chemistry, then the number of potentially life-bearing worlds in the galaxy is larger than the most pessimistic estimates suggested. Let's pause for a moment and consider what this really means. The far side of the Moon, that perpetually hidden hemisphere staring into the cosmic dark since before Earth had continents, is not merely a piece of geology, it is an instrument, a measuring device calibrated by 4.5 billion years of uninterrupted record-keeping for understanding how life emerges in the universe. We sent a robotic rover to drive across it. We are now returning its rocks to our laboratories. We are building the seismic networks to map what lies beneath it. And each layer of understanding we extract brings us closer, not just to the Moon's story, but to our own. But there is another dimension to the far side's significance, one that is almost entirely practical and that will become increasingly important in the decades ahead. The far side of the Moon is the quietest place in the inner solar system. Electromagnetic quiet, radio quiet. Earth generates an enormous amount of radio frequency noise, from telecommunications, broadcasting, radar, satellites, devices of every description. This radio noise fills the space around Earth in all directions. Anywhere in the inner solar system within range of Earth's radio emissions, that noise is present as background interference, except on the far side of the Moon. With the bulk of the Moon itself interposed between the far side and Earth, the electromagnetic noise from our civilization simply cannot reach the far side's surface. It is blocked, shielded. The far side is, in radio terms, the most pristine natural environment accessible from Earth, a silence that no location on Earth or in low Earth orbit can match. Radio astronomers have dreamed for decades of placing telescopes on the lunar far side. A radio telescope there would operate without interference from Earth's technological emissions. It could observe frequencies that Earth's ionosphere, the upper layer of our atmosphere, reflects and absorbs, making them invisible to ground-based observatories. It could peer at the universe in wavelengths that have never been cleanly observed from Earth. In particular, it could observe the cosmological 21-centimeter signal, the radio emission produced by neutral hydrogen atoms in the early universe, from a period called the Cosmic Dark Ages, before the first stars had formed. This signal, dating from approximately 380,000 to 800 million years after the Big Bang, carries information about the conditions of the early universe that no other observation technique can access. It has never been cleanly detected because Earth's ionosphere and human radio emissions contaminate every attempt at ground-based observation. A far-side telescope would change that, completely. NASA's Lunar Surface Electromagnetics experiment, combined with proposed concepts like the Lunar Crater Radio Telescope, a concept selected for study under NASA's Innovative Advanced Concepts program, which envisions deploying a wire mesh radio telescope inside a natural lunar crater on the far side, potentially a kilometre in diameter, could open an entirely new observational window on the universe. The scientific return from such an instrument would be extraordinary. Observations of the cosmic dark ages would directly constrain models of the Big Bang, of inflation, of the formation of the first stars and galaxies. They would potentially reveal signatures of physics beyond the standard model. They would answer questions that no current or planned telescope, not JWST, not the extremely large telescope under construction in Chile, not the Nancy Grace Roman Space Telescope, can address. The far side of the Moon, in this context, is not just a record of the past. It is a platform for understanding the universe's deepest history. China recognized this. The Queqiao relay satellite deployed for Chang'e 4 was not just a communication infrastructure investment. It was the first step toward permanent far-side access. The International Lunar Research Station, a joint China-Russia initiative targeting the lunar South Pole region for the 2030s, includes far-side science as a component. NASA's Artemis program, with its Gateway station planned for lunar orbit and its South Pole surface missions, establishes infrastructure from which far-side access becomes progressively easier. The Moon is transitioning from a destination, the endpoint of Apollo-era ambition, to an infrastructure node, a scientific platform, a gateway, and the far side is the most scientifically valuable part of it. There is one more thread to follow, one more implication that draws the geological, the astronomical, and the existential together into a single coherent picture. Return to the South Pole Aitken Basin. Return to that buried mass. That anomaly of 2.18 quintillion kilograms, sitting in the far side mantle like a question mark written in iron and nickel. Whatever its origin, impactor remnant or magma ocean product, it represents the deepest interior of the Moon that we have ever had the potential to directly sample. Future missions to the SPA Basin, with drills capable of reaching 40 or 50 kilometers depth, would enter territory that is, in a very real sense, geological time travel. The rocks at that depth formed in the first 100 million years of the solar system's existence. They predate the late heavy bombardment. They potentially predate the conditions that made Earth habitable. They are older than anything accessible anywhere else on the surface of a world humans can visit. Those rocks carry isotopic ratios that date from the formation of the solar system itself. They carry the chemical fingerprints of the processes that produced our Sun's planetary system from a collapsing cloud of interstellar gas and dust. They are, molecule by molecule, part of the original construction material of everything, including us. Carl Sagan famously observed that we are made of star stuff, that the atoms in our bodies were forged in stellar interiors and scattered by supernova explosions across the galaxy, to eventually condense into the solar nebula from which our Sun and planets formed. The rocks beneath the South Pole Aitken Basin are made of that same original material, the residue of the same stellar generations that produced the atoms in your body. They are, in the deepest possible sense, our relatives. To sample them, to date them, to analyse their chemistry, is to read our own origin story. We began with a lie, or rather, with a structural truth so peculiar it functions like one. Every map of the Moon you have ever seen shows half the story. For the entirety of human civilization, from the first prehistoric person who looked up and traced patterns in the lunar face, to the Apollo astronauts who walked its near-side plains, the far side remained unseen, unknown, a perpetual mystery maintained by the universe's own geometry. When we finally looked, when China's Chang'e 4 settled onto the ancient floor of Von Karman crater in January 2019 and became the first human-made object to rest on that hidden surface, the mystery didn't end, it deepened. Because what we found on the far side and beneath it, and encoded in its ancient rocks, was not the alien strangeness we half expected. It was familiarity of the most profound kind. The far side holds the record of how we got here. The asymmetric formation of the moon, driven by the heat of the Theia impact. The SPA basin collision that excavated the mantle and reshaped the hemisphere. The late heavy bombardment that delivered water and organic chemistry to a young Earth. The geological conditions that, within a geologically brief window of time, allowed chemistry to cross the threshold into biology. Every chapter of that story is written in the rocks of the far side, in the craters and basins and ancient highland plains, and, most remarkably of all, in the invisible mass buried 40 kilometers deep in the lunar mantle. Massive, ancient, impossible to fully comprehend in human terms, and yet precisely legible to those with the instruments and the patience to read it. Chang'e 6's returned samples are in the laboratories now. The seismic networks are being designed. The far-side radio telescopes are being proposed, modelled, funded in early stages. The Artemis program is building the infrastructure that will, within the next decade or two, make sustained scientific work on and around the moon possible in ways that were unimaginable during Apollo. We are at the beginning of the era of lunar science, not the end of it. And as we continue to dig into those returned samples, as the first seismometers wake up on the far side surface and begin listening to the deep moonquakes propagating through that buried anomaly, as the first radio telescopes begin to hear the faint whisper of the cosmic dark ages from their position behind the moon's radio shadow, the far side will continue to give up its secrets. One thread remains unresolved: the mass beneath the South Pole Aitken Basin. Impactor remnant or magma ocean product? The answer is not yet in. The data from Chang'e 6 samples may begin to distinguish between these possibilities. Future seismic networks will image the structure directly, and when that answer arrives, it will not close the story of the far side, it will open the next chapter. Because every time we look more carefully at the moon, it turns out to be hiding something new, something ancient, something profound, something that, in the end, is always about us.